I thought that this would be a good time to just briefly go over the highlights from Chapter 8 in preparation for your testing, concentrating on the counting principles and then how that relates back to the probability. Um, I would call the first part of this advanced counting techniques. And the first of those is the multiplication principle. The multiplication principle simply says if a series of choices is made, the total number of distinct ways that you can make that series of choices is just the product of the number of ways that each individual choice can be made. And I always like to think of this as a tree diagram, even if it's too big to actually draw. For instance, in this problem it says if an outfit consists of a coat, shirt, tie, and pants, and if John has 2 coats, 3 shirts, 2 ties, and 1 pair of pants, they're going to be 2 times 3 times 2 times 1, each of the individual number of ways, and that would be a total of 12 different outfits that John could wear. And to visualize that as a tree, you would say, well, John can wear either of 2 coats, and once the choice of coats is made, if John chooses coat 1, there are 3 different shirts he can wear. If he chooses coat 2, there are 3 different shirts he can wear. And once those 2 choices are made, there are 2 ties that can be chosen for each of the other choices. And then there's 1 pair of pants. And if you count those are 12. That's the multiplication principle. Secondly, factorials. Factorials count the number of ways to put a set of distinct objects in order, and the symbol is a number with an exclamation point following it. It simply means to multiply starting at that number n down by 1 until you get to 1 and take the product, with the caveat that 0 factorial does not follow that pattern, but 0 factorial is defined to be 1. For example, if you had 3 factorial, that would be 3 times 2 times 1. That means there would be 6 different arrangements of, say, for instance, 3 letters A, B, and C. Thirdly, if you want to count distinct arrangements of objects when they're not all different, you've got to divide out the factorial of the number of times each object is repeated. For example, if you take the letters in the word assistant, that's 9 letters. If all the letters happen to be different, that would be 9 factorial distinct arrangements. However, since there are 2 A's, 3 S's, and 2 T's, you've got to divide out 2 factorial times 3 factorial times 2 factorial. 2 factorial for the A's, 3 factorial for the S's, and 2 factorial for the T's. The fourth thing is permutations. The permutation of n things taken r at a time is defined to be n factorial divided by the difference between n and r factorial. Permutations count the number of ordered arrangements of all possible subsets for certain size from a set of distinct objects. For example, there would be 5, choose 3. There would be 5 taken 3 at a time. 5 factorial over 5 minus 3 is 2 factorial, which would come out to be 60. 60 different arrangements of the letters A, B, C, D, E, if you take them 3 at a time. In other words, any 3 at a time, A, B, C, A, C, B, just pick any combination, or not combination, any permutation of those 3 letters, but only taking them 3 at a time out of a group of 5. You can also solve the same problem using multiplication principle. The multiplication principle is a more basic thing, so you can quite often go back to it even if you can use some other technique. By the multiplication principle, there are 5 ways to choose the first letter, there are 4 ways to choose the second letter once the first letter is chosen, and there are 3 ways to choose the third letter once the first 2 letters are chosen. And you notice that's the same answer as you got using your formula for permutations. Fifth thing, a permutation, when the subset is the whole set, is the same as a factorial. In other words, the permutations of n things taken n at a time is just n factorial. If you try the formula, you'll find out, for instance, if you just took permutation of 4 things taken 4 at a time, and compare it to 4 factorial. If you use the formula 4 things chosen 4 at a time, you end up with a 0 factorial in the denominator, which is defined to be 1, and you just end up with 4 times 3 times 2 times 1 over 1, which is 24. And if you do 4 factorial, you get the same thing. So a permutation where the subset that you're using is the size of the whole set is just going to be the factorial of that. Combinations. We've used different ways of writing combinations. We use n over r in parentheses. We use c n comma r. But either way, all that means is n factorial divided by r factorial with another factor in the denominator that's the difference between n and r factorial. In other words, the combination formula is the same as the permutation formula with the r factorial thrown in as a second factor in the denominator. And combinations count the number of ways that subsets of a set of objects can be chosen when order is not important. And with permutations, order is everything. With combinations, we're just choosing. We don't care what order. For example, there are 5 choose 3. A combination of 5 things taken 3 at a time would be 5 factorial over 3 factorial with an additional factor 5 minus 3 factorial, and that turns out to be 10. 10 different 3-person committees that can be formed from a group of 5 people. And again here, order is not important. It's just which 3 people are chosen. There's some useful facts about combination that you don't necessarily have to know because you can just use the formula, but if you know them already, it saves you a little bit of time. Anything taken with a 0 combination with 0 or with the number itself is always going to come out to be 1, and anything taken in combination with 1 or 1 less than itself is always going to come out to be whatever n is. For example, if I take 5 choose 0, combination of 5 things 0 at a time, it'll always come out to be 1 no matter what that number is, whether it's 5 or 50. And when the numbers match, you're always going to get 1. And no matter what the top number is, if the bottom number is 1, the top number will be the answer. And if the bottom number is 1 less than the top number, the answer will always be the top number. As we just discussed, you can use some of these combination facts to make it easier and faster to do these calculations, but when you're doing calculations that don't fit any of those facts, you could also use Pascal's triangle if you'd like, as long as the n value is not too large. And to do Pascal's triangle, the edges always are 1s, but any number in the interior of the triangle is the sum of the 2 numbers above it. So 2 is 1 plus 1, 3 is 1 plus 2, 3 is 2 plus 1, 6 is 3 plus 3, 5 is 1 plus 4, and 10 is 4 plus 6. And you can extend that triangle as far as you want. And the way you use it is that the ones don't tell you anything on the edges as far as which combination you're doing, but the second number does. The second number in each row is the value of n. So in other words, here I'm looking at the top number being a 5, and the smallest value of the bottom number is 0. So this is 5 choose 0 and it's 1. This is 5 choose 1, which is 5. This is 5 choose 2, which is 10. 5 choose 3 is also 10. 5 choose 4 is 5. And 5 choose 5 is 1. And you can carry this triangle down as far as you want if you decide you want to use that for fairly small values. And of course you don't have to. You can use the calculator. On this summary handout for Chapter 8 had to do with advanced counting techniques. But now that, assuming that you've grasped that and you can count things better, it allows us to go back and solve some more interesting probability problems. So the 8th thing really starts off with recalling something we already know, but just as a reminder, the basic probability principle underlies almost every probability problem that we're going to look at, and it says for an event E and it's equally likely, which is important, an equally likely sample space, the probability of E is equal to the number of elements of E divided by the number of elements in the whole sample space. Now, if you want to think of that in more concrete terms, you might say that the probability that you get a desired outcome is simply the number of ways the desired outcome can occur divided by the number of ways that any outcome in the sample space can occur. That's the basic probability principle. For example, if you draw one marble from a bag that has 5 red and 3 black marbles, according to the basic probability principle, which applies because if they're randomly selected, it's equally likely to choose any one marble. The basic probability principle says the probability of getting a red marble is the number of red marbles divided by the total number of marbles. Well, there are 5 red marbles in the bag, and there are a total of 8 marbles in the bag. That's the basic probability principle. Then you have the product rule of probability. It says the probability of an event E and an event F occurring together is the probability that E occurs times the probability that F occurs given that E occurred. Now, if those two events are actually independent of each other, the conditional part has no effect and you can just leave it off, and you can say for independent events the probability of E and F is just the probability of E times the probability of F. And as I've mentioned before, to me it's useful to think of this product rule visually in terms of a tree diagram, even if you don't actually write it out. For example, from a bag of 8 marbles with 5 red and 3 black in the bag, what is the probability of randomly drawing a red marble, then a black marble, and finally another red marble? I again think the tree diagram is the best way to handle that. So you might actually just draw it out. And if you don't draw it out, you still might think about it as a tree diagram. So before you take the first draw the first marble, there are 1, 2, 3, 4, 5 reds and 3 blacks. So in the beginning, the probability of getting a red marble is 5/8, and the probability of getting a black marble is 3/8. And if you draw that as a tree, the first choice, the probability of getting a red is 5/8, the probability of getting a black is 3/8. Now, before you make your second draw, you got to look at whether you got a red the first time or a black the first time. If you got a red the first time, then there would only be 4 reds and 3 blacks, a total of 7 marbles. So the probability that the first one, the second one is red, if the first one is red, is 4 out of 7. 4 reds out of 7 total. And the probability that the second one's black, given that the first one was red, is 3 out of 7. And again, those probabilities would go here. But if the first marble is black, then you've still got the 5 red marbles, but you only have 2 black marbles. So the probability that the second one was red, given that the first one was black, is 5 out of a total of 7. And the probability that the second one was black, given that the first one was black, there are only 2 blacks left, so there's 2 out of 7. And again, those would go on the branches down here where the first choice was a black. And if you go all the way through these calculations, I'm not going to do them all, you're going to see that your branches are going to look like so. The main point is you really don't have to label them all because we're looking for a particular branch. We're looking for the probability that the first one was red, then the second one was black, and then the third one was red. So that's this branch right here. And as we discussed, whenever we calculate the probability of something that represents a branch on the tree, we multiply. So if you multiply those 3 probabilities, you end up with 5/8 times 3/7 times 4/6. That comes out to 60 over 336, which is 5/28 when you reduce it. And you could reduce this before you even multiply it if you wanted to. You can see that 4/6 reduces to 2/3. So that's the probability we're looking for, and I think the tree diagram helps us visualize that better. Now, just a couple of notes. I just want to drive this home because some people have trouble remembering when things apply and when they don't. 3 things. We're drawing without replacement. That's why the probabilities are changing on the branches from reds to blacks and why the reds are not always the same. And I guess I've already mentioned this, but I'll say it again. You don't really have to draw the tree diagram. Even if you don't draw it, you might visualize it. And finally, the probabilities in all the branches after the first set are actually conditional probabilities. So this probability here is the probability that the second draw is a black, given that the first one was a black. This probability here is the probability that the second one was red, given the first one was black. They're all conditioned on what happened earlier. We've actually talked about some special types of probability density or distribution functions. PDFs is what, as I call them. The most important one for us is the binomial. For the binomial PDF, if you let n stand for the number of trials, x the number of successes, whatever it is you're trying to do, whatever you're trying to get, that's a success. And if p is a probability of success, then the probability of x successes is a combination of n things taken x at a time times the probability p raised to the x power, these two numbers match, multiplied by 1 minus p raised to the difference in these two numbers, the difference between n and x. Notice that the powers always add up to n, and the two probabilities here, when all is said and done, had better add up to 1. Now, when do you use binomial? I would say the most important clue in knowing when to use binomial is whether or not the probability of success is the same from trial to trial. If it is, then you're going to be able to do this as a binomial problem. For example, if 3 marbles are randomly selected from a bag containing 8 marbles, 5 red and 3 black, what's the probability of drawing exactly 2 red marbles if we draw with replacement? Now, if we pull these out and leave them out as we keep drawing, it goes back to the tree diagram technique, and it's not binomial. But if you put a marble back, note its color, and draw again with replacement, this is going to be binomial. The probability of getting a red will be the same every time. And since there are 5 reds out of a total 8, that probability of success being getting a red marble, is going to be 5/8. You're doing it 3 times, 3 marbles selected, and you want to know the probability of getting exactly 2 reds. And again, x is the number of what you're looking for, the number of successes you're looking for red, so success is getting a red. If you take those values and plug it in, I won't belabor the arithmetic, you do need to practice this, but 1 minus 5/8 is 3/8, and 3 minus 2 is 1, and you end up with 225 over 512. If a problem asks you to leave it as a fraction, you'll leave it that way. It doesn't reduce, but if it did, you'd need to reduce it. If it asks for a decimal rounded to 3 decimal places or 4, you do that as well. You do whatever it tells you to in terms of leaving the answer the way it should be. 11, when you're calculating probabilities and you're not doing replacement. Now, in these problems, without replacement means it's definitely not binomial. Now, if it's not binomial, it really harks back to the probability principle, the solution technique. Because the probability changes from trial to trial, and you cannot use the binomial. The basic probability principle says the probability you get a desired outcome is the number of ways the desired outcome can occur divided by the number of ways any outcome in the sample space can occur. Now, because we're doing subsets where order doesn't matter, we're going to have to use combinations to count these number of things, number of ways something can occur thing, in both the numerator and denominator. For example, if you have a problem that says if 3 marbles are randomly drawn from a bag containing 7 marbles, of which 4 are red and 3 are black, what is the probability of drawing exactly 2 red marbles? Now, this time it's not a binomial because we're drawing without replacement. What do? Basic probability principle says the probability of getting exactly 2 red marbles out of 3 is the number of ways to get 2 red marbles and 1 black. Now, notice I added this and 1 black because when it says exactly 2 red marbles and you're drawing 3, The implication is you still have to draw another marble, and it can't be red. So really you're drawing 2 reds and 1 black, even though it was only implied over here. If you're drawing 3 and 2 of them are red, the other one has to be black. And down bottom you've got the number of ways where you don't care what color they are, so there's a number of ways to get any 3 marbles. This and inevitably means multiplication, so you're going to multiply the number of ways to get 2 red by the number of ways to get 1 black. Well, these are combinations. You want to choose 2 reds out of the 4 reds that you have. Remember, there are 4 reds. And you want to choose 1 black out of the 3 blacks that are there. And down bottom, you're still drawing 3, but you have 7 marbles if you don't care what color they are. Now, just a couple of things. These two numbers, 4 and 3, better add up to 7, and these two numbers, 2 and 1, better add up to how many balls you're drawing. And these, and also to the bottom number in the bottom combination, 2 and 1 is 3. And if you do these calculations, you'll end up with 18/35. This problem that I just solved by the basic probability principle can also be expressed as a PDF, although we've never really done it that way formally. I think some of you might actually benefit from thinking of it that way, and I'm going to go ahead and present it. If you don't want to use it this way or think of it this way, that's fine, but I'm going to throw it out there. This PDF, when you actually write this out as a PDF, is a PDF called the Hypergeometric, and it's basically for the situation that we did with the binomial when you had width replacement, except that you're throwing out the with replacement and putting in without replacement, and then it becomes a hypergeometric. And I have to introduce a couple of variables to make this formula work out. Suppose I have A of the things I'm looking for. Like in the previous problem, I was looking for red marbles, so A would be the number of red marbles in the bag, and B is the rest of the stuff. In this case, they're just blacks, so B would be the number of black marbles in the bag. And I'm still choosing N total items, just like I've been using N, and X of them, just as I've been using X before, X of them are the things that I'm looking for. And if I do all that and define these new variables, I can define this hypergeometric distribution as the probability of getting X of the things I want, and that is a fraction with A of the things I want, like A red marbles, and I want to choose X of them from the A, and the rest of the things I'm choosing would be N minus X, have to come from the things that aren't red, or whatever the A stands for. And down bottom, I don't care what color they are, or whether they're desired or not desired in general, so I just add up the two amounts, A and B, and I'm choosing N things, so it's going to be N, and notice that X plus N minus X just adds up to N as well. And that's what we've been doing before, but that's expressed this way, you can actually think of this as a PDF, and it has a name. It's called the Hypergeometric. Let's solve that same problem that we just worked a minute ago using the basic probability principle. This time let's think of it as a hypergeometric PDF. We still have 3 marbles to be selected from a bag. There's still 4 red and 3 black, and we want to find the probability, just as before, of getting exactly 2 reds. So here A is the number of red marbles, because that's what we desire, red. That'd be 4. The rest of the marbles are the non-red ones. In this case, it'd be the black ones, it'd be 3. We're choosing 3 marbles, that's what the N is, and we want to know the probability of getting exactly 2 red marbles, so X is 2. Now, if you take those values and plug them into this thing I'm calling a hypergeometric PDF, you'll see that A is 4, X is 2, B is 3, that's how many non-red marbles there are. 3 minus 2 is going to be 1, and down bottom you don't care what color the marbles are, so you choose 3 from any of the 7. And if you simplify these combinations, you'll get 18/35, and that's the exact same answer we got before. So I'm just throwing it out there for you. You don't have to use the hypergeometric, but you can. Totally up to you. So we've talked about specific PDFs. Now I want to talk about just PDFs in general, which may or may not be expressed as a formula, and the concept of expected value. So number 12, generally speaking, a PDF is simply a listing of each possible value that a random variable can take on, maybe call that random variable X, along with the probability of that particular value occurring. The binomial and what we've just recently defined as the hypergeometric can be written as formulas, and there are lots of others. where when you plug in an x, it gives you the probability, and that is a PDF in that same sense. You plug in an x, you can figure out the probability of that x occurring. It's nice to have that, but it's not necessary. In fact, it's pretty common just to have a PDF written as a table. Say, for instance, I have this example. For a $2 payment, Pam can try to guess which number will come up on the roll of a single die. If Pam wins, she gets her $2 back, and then she wins an additional $5. She gets her money back, and she makes a profit of $5. If she does not win, she just loses her $2 bet. Now I can couch this as a PDF, and I can write it as a table where I match up the X value, which is the expected winnings for Pam, with the probability of that thing occurring. Now basically there are only two things that can happen. This is a fairly simple one. If X is the expected winnings that Pam has, she can do one of two things. If she loses and guesses wrong, she loses $2. That's a minus sign, so it's a negative $2. If she wins, she gets her $2 back, so she's even there, and then she wins an additional $5. So there's only two things that can happen in this little simple game. Now what's the probability of that happening? Well, on a die roll, if she's guessing one of the 6 numbers, she has a 1/6 chance of getting it right, which means she has a 5/6 chance of missing it. So the X values are the expected winnings for Pam, and the probability of either of those two things occurring is given right below. That's a perfectly normal PDF. It's not given as a formula, but it's given as a table. Alright, 13. The expected value of a random variable x, denoted by capital E of x, is a weighted average. It's just a weighted average of the x values, and the weights are the associated probabilities. It's kind of like weighting your various quizzes and homeworks and test grades to get your course grade. Everything doesn't count the same, and that's the idea here. If you want to write it out formula, you can think of the possible x values as x of 1, x of 2, all the way to x of n, and their associated probabilities are p sub 1, p sub 2, all the way to p sub n. Then what you do is you take each thing that can happen, multiply it times its associated probability of that happening, and add them up. Now that formula can be realized in practical terms when you have a table by just taking the table, say this one for instance, and adding an x times p of x row, doing the products in that additional row, and then summing those up. That's all this formula is saying. So for instance, for that PDF that I just did, if I were to do the expected value, I would just add a row called x times p of x, and I would multiply. Minus 2 times 5/6 would be minus 10/6, and 5 times 1/6 would be 5/6, and then I would add up all those products. In this case there are just 2 of them. So the expected value of x would simply be negative 10/6 plus 5/6, which would be negative 5/6. Notice it's a negative 5/6. So that means it's an expected loss. So in the long run, Pam is going to lose money if she plays this game over and over again, making that bet. It's a losing proposition in the long run. And the 14th item, and the last thing on the chapter summary for chapter 8, are the special cases. If you have a binomial PDF, the expected value will always be n times p. You don't have to do a table calculation. You could write it out and do it that way, but it's always going to be n times p. Just as an example, if we go back to that problem we did in item number 10 earlier, we had n equals 3 and p equals 5/8, and if you take 3 times 5/8 you get 15/8, and if you'll look back you'll see if you actually took the time to write out the table and write out the x values or probabilities, if you actually did that, you would get 15/8, but it would take you a lot longer and you'd have more of a chance of making a mistake. So if you're given a binomial as a PDF formula, it's much better to try to do this than to write it out as a table and do the long calculation. And now that we've talked about the hypergeometric, it turns out that the hypergeometric is also n times p if you define things properly. You know, when you draw without replacement, after the first draw, the probabilities change. But if you define P as being the probability of success before you start drawing a second and third time, if you define P that way, then the expected value for the hypergeometric is also n times P. So if you look back at that number 11 that we looked at a minute ago with the PDF, n was 3 and P was 4/7, so that expected value would be 3 times 4/7, which would be 12/7. Again, you could write this thing out as a table. In fact, it may be given to you as a table. If you recognize it's hypergeometric, you can use the formula, but you can always do it by the table method as well.